Objective 3 is on the second derivative test, which talks about the concavity of a function. I'm going to start by reviewing the first derivative test and what it tells us. So the first derivative test tells us two things. First, it tells us where the function is increasing, decreasing, or constant. And secondly, from that, it tells us where to find local extrema. The second derivative test will tell us two things about the concavity of a function. So first, it will tell us where the function is concave up, concave down, or has no concavity. And the second thing is it will tell us the location of any points of inflection. And we'll get into what those things are now. So I'm going to demonstrate this with some graphs. So our first function we want to draw be like an upward-facing parabola. Okay. If it's hard to tell that this function is concave up, which it is, we're going to think about drawing tangent lines along this curve. So if I pick any point on my curve and draw some tangent lines along it, what I'll notice is that all of my tangent lines lie under this curve. What that tells us is that the curve is concave up. So concave up, like an upward-facing parabola, that should be pretty easy to remember. Or if we think about tangent lines that lie under the curve, means our function is concave up as well. So of course, another scenario is my downward-facing parabola. So our function here is concave down. We can do the same thing and draw some tangent lines along this curve, at any point. And what we'll notice is that every tangent line we draw along this curve should lie above it. So tangent lines that lie above the function means the function is concave down. And that's it. It's either concave up or concave down, or my function does maybe have no concavity, such as a line. A line would have no concavity, just like our tangent lines don't have concavity. But there is one more instance we should look at. And that was the second thing I told you about, locations for points of inflection. So let's look at a graph that has a little bit of both. So maybe some type of a cubic function here. Part of my graph is concave down, and part of that graph is concave up. And so we're going to make some tangent lines here. So I can see under the curve, concave up. Over here, under the curve, concave up. At some point, it switches to concave down because my tangent lines are now above the curve here. So typically, that change occurs somewhere in the middle between the max and the min. I'm going to say about here in the middle, there is one specific tangent line you could draw where part of that line is above the curve and part of that line is below the curve. And so this point where that tangent line touches is known as the point of inflection. All right, so we're going to get into the second derivative test for concavity. What does that look like, and what are we going to do? All right, so let f be a function whose second derivative exists. We're going to end up with our three cases here. So first, if our second derivative is positive on an interval, then our function f is concave up. Right? Second, if our second derivative is negative on an interval, then the function is concave down. Be our second case. So, of course, the third case is that it's possibly a function that has no concavity. So that would be if our second derivative were equal to 0 on an interval. That's our second derivative test. We're going to look at a few examples here. And we're looking for where function is concave up or down by using the second derivative test. We also want to locate any points of inflection. So our first function, f of x, is x to the fourth minus 6x squared plus 7. So step one, we need to get to our second derivative. So we're going to start by taking our first derivative, or x cubed minus 12x, and the derivative of 7 is 0. And moving on to our second derivative, we get 12x squared minus 12. Similar to the first derivative test, we were looking there for critical numbers, and those were places where either the function wasn't differentiable or where the derivative was equal to 0. So we're going to do kind of the same thing here. We're looking for anywhere our function might not exist, which this is a nice polynomial function, so it exists everywhere, and anywhere where our second derivative is equal to 0. So Set this equal to 0, and we're looking for test values. They're not called critical numbers here. They are potentially points of inflection, but we won't know that yet. Okay? So solutions here, plus and minus 1. So these are our test values. These are the values that we're going to put on our second derivative number line to test the intervals. So step 1, we found the zeros of our second derivative. We would also note anywhere where the function didn't exist. Okay. Step 2, we're going to do our second derivative number line test. So once again, it's important to label every number line you're working with. Here, it's our second derivative test, so we label it f double prime. On here, we have -1 is a 0 of the second derivative, and 1 is a 0 of the second derivative. Then we just need some values to test. We'll pick some numbers here. Remember, you're plugging those into your second derivative. Okay, and we're looking for positive, negative, or equal to 0. So if we plug in -2 to our second derivative, we're going to get a positive. If we plug in 0, we'll get a negative. And plugging in 2 will also result in a positive. So now this is our second derivative test. So if we interpret these results, what's happening to function f here? F is concave up on the first interval, down on the second, and up on the last. And we'll write those out. So concave up, negative infinity to -1, 1 to infinity. F is concave down from -1 to 1. So again, a point of inflection is a point where our concavity changed. So did we have points where the concavity changed here? Yes. We went from concave up to concave down at -1, and we went from concave down to concave up at 1. And so those are both points of inflection. So POI, POI, and we'll go ahead and write that out as our third step. Points of inflection, when x is -1 and when x is 1. That finishes our first example. All right, so moving on to example number 2. This time our function gets a little more interesting, 2x minus sine x. Nice thing for us here, we're dealing on a specific domain, -pi to 2pi. So we don't have to look at the entire graph from -infinity to infinity here. Okay. So keeping that in mind as you do your intervals, we're going to go ahead and do our first then second derivative. First derivative is 2 minus derivative of sine is cosine. And then we'll move right along to our second derivative. Remember to also look for anywhere where the function may not exist. 2x has all reals, sine x has all reals, so we're good here. Derivative of 2 is 0. The derivative of negative cosine is going to give us sine. And then we're setting this equal to 0. So from -pi to 2pi, but not including those endpoints, when does sine equal 0? These will be our test values. So this happens at x equals 0 and x equals pi. These are the only two values that are within our interval. So watch out for other given intervals on other problems. Okay, that was step 1. Next thing we want to do is our second derivative test. So we'll set up our number line for f double prime. Okay. Now we don't want to test over all reals, so you want to make sure that you stay within the interval again. So this is going to cut off at -pi and up here at 2pi. So in between, we'll put our 0 is a 0 of the second derivative, and pi is a 0 of the second derivative. Right. My second derivative, remember, is sine. So if you're traveling from negative pi to 0, you're in quadrants 3 and 4, where sine has a negative value. So we're going to get a negative here for anything you plug in. Okay. That's because, again, we're in quadrants 3 or 4. Then traveling from 0 to pi, you're in quadrants 1 and 2. So any angle you plug in here will give you a positive for sine. And then we're back to quadrants 3 and 4, where sine is, again, negative. We can interpret this for our function. We have f is concave down, concave up, and concave down. So concave up only from 0 to pi, concave down from negative pi to 0, and pi to 2 pi. Again, staying within the interval, so it's not all real values. Okay, third, points of inflection. Anywhere where the concavity changes, so we do have points of inflection when x is 0 and when x is pi. So we have one more example to go. All right. We have to pay attention to anywhere where the function may not be differentiable. So that's going to happen at positive and negative 2. So these should be test values that we're going to use. They would be used for the first or second derivative test. Then we want to also find anywhere where our second derivative is equal to 0. We do have to do our first derivative and then get our second derivative. First derivative quotient rule. Right. And before we do our second derivative, we want to clean this up. So let's see, we could factor out a 2x, but we might just want to go ahead and multiply everything out and combine our like terms that way. So that's 2x cubed minus 8x, then minus 2x cubed minus 2x. So that worked out pretty nicely there. That's going to reduce down the 2x cubed gone, negative 10x over x squared minus 4 squared. So there's my first derivative. Now I need my second derivative. So we're going to do our quotient rule again. So low d high, we get negative 10. Minus high d low. So we have to be careful here when I do the derivative of the denominator. We're going to be doing our chain rule. So we're going to start with the power rule here. Bring 2 down and drop the power by 1. And the derivative of what's inside, 2x. Okay, all over the square of what's below. So x squared minus 4 now to the 4th power. All right, so let's take out what the two have in common. I think that's going to be an easier way to do it this time. So they do both have a negative 10, and they both have an x squared minus 4. So factoring that out, negative 10 is gone. One more x squared minus 4 is left. Okay, over here the negative 10 was taken out, so it's a negative x times 4x. Negative x times 4x is going to give us negative 4x squared. Right. So we do need to just simplify what's inside there, and I can reduce on the outside here. One of these terms with 1 here is 3 on the bottom, and what's left on top? Negative 10 times, what's that? 1 minus 4 is negative 3x squared minus 4 over x squared minus 4 cubed. And I could just take the negative in here out, and that just makes everything positive. Now, once I have my second derivative, we're supposed to set this equal to 0 and solve. And only fractions equal 0 when the numerator is 0. So looking for anywhere where the numerator equals 0, 10 is not going to help. We set 3x squared plus 4 equal to 0. And you'll notice x squared is going to end up being equal to a negative number. That's not going to produce any real values. So we're not going to get any zeros for our second derivative. And that was a lot of work to figure out that my only test values are 2 and negative 2. So step 2, we want to test our second derivative. Negative 2 and 2 are placed on here. Now, these aren't zeros of my second derivative, but they're places where the function doesn't exist. So it's where my second derivative also doesn't exist. Okay, and then we'll test in our intervals. So some test values here. Okay, and plugging those into our second derivative here. Okay, plugging in negative 3, the top's going to be positive no matter what. Negative 3 squared minus 4 cubed is also positive. Okay, we'll get the same result from plugging in positive 3, since we're squaring it each time. And then if I plug in 0, we're going to get a positive on the top. Negative 4 cubed is a negative on the bottom. So that tells me my function f is concave up, then down, then up. So concave up from negative infinity to negative 2 and 2 to infinity. Concave down from negative 2 to 2. And as far as points of inflection go, we can't really say these are points of inflection since they're vertical asymptotes. We don't actually have points on the function that exists here. So while there are places where the concavity changes, they're not actually any points, so we can't call them points of inflection. So we're just going to leave it here.